Hello. Welcome to devlog number 11. In the previous devlog, I reached out to exercise 84, and I think after that we realized a bunch of these Zigling challenges are going to be skipped because of the fact that the async feature is not implemented in the uh, Zig's self-hosted compiler. I don't know what that means yet. However, I decided to move forward for whatever that is available and then get back to this to resolve that. For that reason, I'm tracking it down here, and we are jumping to exercise 92. So after a sip of coffee, evening coffee, after 9 p.m., hopefully it keeps me recharged to have another nice experience doing Zig exercises. So exercise 92, interfaces. Remember our ant and bee simulator constructed with unions back in exercises 55 and 56. I barely remember it, but that's fine. I think I can check it if needed. There we demonstrated the unions allow us to treat different data types in a uniform manner. One neat feature was using tagged unions to create a single function to print a status for ants or bees by switching. Yeah, now I remembered it. Here we were creating enum type, and then it was able to automatically switch between them and pick up the right value. Well, that simulation was running just fine until a new insect arrived in the virtual garden, a grasshopper. Dr. Zoroptera started to add grasshopper code into the program, but then she backed away from her keyboard with an angry hissing sound. She had realized that having code for each insect in one place and code to print each insect in another place was going to become unpleasant to maintain when the simulation expanded to hundreds of different insects. Thankfully, Zig has another comp time feature we can use to get out of this dilemma called inline else. Okay, we can replace this redundant code with a special A inline else normal T. Okay, we can have a special handling of some cases, and then Zig handles the rest of the matches for us. With this feature, you decide to make an insect union with a single uniform print function. All of the insects can then be responsible for printing themselves, and Dr. Zoroptra can calm down and stop growing on the furniture. The this kind of names in English literature is my kryptonite. I don't know why I never stop on these to find the right pronunciation. And every time I read them, uh, this puts a smile in my face. So let's quickly check how does it sound. Maybe bring a browser and then go to translate. Yeah, Slovenian. Oh, Zrapra.
Zaraptera.
Zura. Okay, I know it now. Solved. Okay, let's go to the problem we had. Expected type expression. Okay, that's fine. We have question mark. Constantly, we have an AND type with a print function inside it. Okay, this is different, right? Because before on 55, these insect types were just enums. Yeah, we had insects, and then for the print statement, we were using this kind of cache. And then in, I think, 56, here we created an enum to make it easier and pass the enum to it. And then the easier, there was another version that you could just put enum directly inside union. So every key was considered as an enum. And then here now we are creating a struct instead, and then we have different types, and we grasshopper. Here's the new grasshopper. Notice how we've also added print method to each insect. Yeah, and they are receiving self. It's not a pointer, meaning it's not going to change the state of the struct itself. And then we have an insect union with enum syntax, and each of those has and be and grasshopper. Thanks to inline else, we can think of this print as being the interface method. Any member of this union with a print method can be treated uniformly by outside code without needing to know any other details. Cool. Let's see what's happening here. So we pass self to it. Inline else case that print. Okay, let me finish my coffee. This is not a tasty one, but yeah. Okay, I think I understand it, right? When we define an insect, which is a union, it means we define one of these three types, right? And in terms of enum, it means it's easy for them to be picked in a switch statement like scenario. However, we are adding a print function to this where we have the switch, and instead of matching these one by one, we are matching all of them and then invoke their case. But I'm wondering, why do we even need this? Okay, I'm going to break this, but let's first fix the problem. Pubfn main void const my insects, right? And then we have an insect and that is still alive. Bee flowers visited, distance topped, and then daily. Almost done. We want to print each insect with a single method call. Is insect dot print. Okay, this works. However, let's try commenting this out, and here just do self dot print. Okay, self dot print here will call this function itself. However, we want to, yeah, exercise 092. Segmentation fault. Core dumped. Okay, this is an infinite call to itself, which we don't want. But basically what it does here is unpacking this object. Okay. Our print method in the insect union above demonstrates something very similar to object-oriented concept of an abstract data type. That is, the insect type doesn't contain the underlying data, and the print function doesn't actually do anything and do the printing. Okay, and it is called abstract data type. Okay, the point of an interface is to support generic programming, the ability to treat different things as if they were the same, to cut down the clutter and conceptual complexity. The daily insect report, it doesn't need to worry about which insects are in the report. They all print the same way via the interface. Yeah. Dr. Zoroptera. Yeah. And then okay, I think I get this one. 93 is the next one. Let's solve that. When Andrew Kelly announced the idea of a new programming language, namely Zig, in his blog on February 8, 2016, he also immediately stated his ambitious goal to replace the C language. In order to be able to achieve this goal at all, Zig should be as compatible as possible with his predecessor. Only if it's possible to exchange individual modules in existing C programs without having to use complicated wrappers, the undertaking has a chance of success. So it is not surprising that calling C functions and vice versa is extremely smooth. To call C functions in Zig, you only need to specify the library that contains the said function. For this purpose, there is a built-in function corresponding to the well-known @import called @cimport. All required libraries can now be included in the usual Zig notation. Now a function can be called via the, in this example, constant C. Beautiful. By the way, most C functions have return values in the form of an integer value. Errors can then be evaluated, return 0, or other information can be obtained. For example, puts returns the number of characters output. So that all this doesn't remain a dry theory now. Let's just start and call a C function out of Zig. And then we import std, we import unistd header file, and then okay, we have write. In order to output text that can be evaluated by Zig Builder, we need to write it to the error output. In Zig, we do this with the debug print, and in C, we can specify a file descriptor for error console. In this exercise, we use write to output 17 character but something is still missing. Is it C dot right? Wow. Also LSV is working with this. I am excited about it. Beautiful. So is that it? There is no catch? We can just call C functions? Something must be considered when compiling with C functions, namely that the Zig compiler knows that it should include corresponding libraries. For this purpose, we call the compiler with the parameter lc for such a program. Okay. This is easy to remember. Nothing drastic. Let's consider this one done. Go to 94. Often C functions are used where no equivalent Zig function exists yet. Okay, that's getting less and less. Since the integration of a C function is very simple, as already seen in the last exercise, it naturally offers itself to use the very large variety of C functions for our own programs. As an example, let's say we have a given angle of 765.2 degrees. If we want to normalize that, it means that we have to subtract x multiplied by 360 degrees to get the correct angle. How could we do that? A good method is to use the modulo function, but if we write that it only works with float values that are known at compile time. In Zig, we would use @mod instead. Let us now assume that we cannot do this in Zig, but only with C functions from the standard library. In the library mass, there is a function called fmod. The F stands for floating and means that we can solve modulo for real numbers. With this function, it should be possible to normalize our angle. Let's go. And then here, I think I need to import in library math.h. This the one. What do we need here? Why we have curly braces here? Let me double check this one. Oh, ow. It's C include. Like this. And a semicolon. Okay, the syntax is a little bit different. We have C import and then C include. And what does it do? Okay, I still have the browser from yesterday open. Zig C includes. Add C includes. This function can only occur inside C import. This appends include pass to C import temporary buffer. And what is C import? This function parses C code and imports the functions, types, variables, and compatible macro definitions into a new empty C struct type, and then returns that type. Expression is interpreted at compile time. The built-in functions C include, C define, and C undefined work within this expression appending to a temporary buffer, which is then parsed as C code. Okay, so it's this cimport is like yeah, Scratchpad where you can write C code, and C include is just importing that code into this. Interesting. 95. The Zig language is in rapid development and continuously improves language constructs. Ziglings evolves with it. Until version 11, Zig's for loop didn't directly replicate the functionality for C style, which are so well suited for iterating over a numeric sequence. Instead, while loops with counters clumsily stood in their place. But here we are in the glorious future of Zig's for loops can now take this form. Okay, we can put a range here. The key to understand this example is to know that 0 to 9 uses the range syntax. At the moment, ranges in loops are only supported in for loops. Perhaps you recall exercise 13, we were printing a numeric sequence like so. I want to print every number between 1 and 20 that is not divisible by 3 and 5. Let's try out the new form of for loop. So basically it would be 1 to 20. Yeah, beautiful. And the next one is 96. Memory allocation, finally. In most of the examples so far, the inputs are known at compile time, thus the amount of memory used by the program is fixed. However, if responding to input whose size is not known at compile time, such as user input via the command line arguments, inputs from another program, you'll need to request memory for your program to be allocated by your operating system at runtime. Zig provides several different allocators. In the Zig documentation, it recommends arena allocator for simple programs which allocate once and then exit. And the syntax, we tried it before in the calculator exercise, but I think and I think this is the same thing, right? So we have an initializer for arena allocator where we pass in a page allocator to it based on heap, and then we denate it after our context. We also have the allocator. We can use this allocator, but we don't need to deallocate these memory creations every time. This init will also deallocate this. Instead of a simple integer or a slice with a constant size, this program requires allocating a slice that is the same size as an input array. Given a series of numbers, take the running average. In other words, each item n should contain the average of the last n elements. Okay, we have a running average function, and then we have a for with range starting from 0 over the items of the array. Okay, this syntax I believe is new, right? We have the range as index over here and then value on the right side. So I remember the other way around, but this also apparently is the same. And then sum plus value, float from integer, ensuring the index turns into float. We add +1 floating index. Oh, this is to help us to make a floating division. An average index would be sum divided by f index. I still believe I don't understand half of this logic here. What's happening? I understand the syntax. I understand what is the requirement, but some of the specifics of the syntax I don't understand why it's used like that. Let's move forward and see how it works. Pretend this was defined by reading in user's inputs. So we have a dynamically allocated array, and we have a pointer to it, storing it in this type. Initialize the allocator, query on exit, initialize the memory allocator, allocate memory for this array. The syntax up here was allocator.create. Expected type. Okay. Or it work like this. Should I do at type of array for this? I am getting out of memory. It's like 64, is it? F64. Okay, first of all, there is a try happening here. Then also I need to define size. Should I? Okay, what's happening here? I need to try it to prevent the out of memory error. And then expected type f64 found a star f64. Let's ask Copilot. Remove this. What's wrong with this? So specific. Let's see how smart AI is. The issue is The issue is that allocator create allocates memory for a single item of the given type, but you are passing a slice type instead of an array type. Allocates the memory for one slice struct, which contains a pointer and length, not for an array of f64. Use alloc with size. Use create for a fixed size array. But here in the allocator, oh, there are two syntaxes. One, you create I32, which is single value, and the other one is allocating for array. Outline, is it? I think it will fail, right? Okay, so since it wants to have an array of f64, I need to allocate. And with allocate, I define the type I want together with the size that I want. Also, I can create when it's a single type. It's a fixed size. All right. Yeah, this summary is good. Create T allocates memory for one type T. Allocate Tn allocates memory for n items of type Tn returns. Okay. For more detail on memory allocation and different types, see this video. Nice of you. Okay, let me pause my music. You play.
Benjamin Feng is not only our first speaker today, but also our first returning speaker ever. Normally, I try to make a joke in the introduction, but this time, all I want to say is thank you, Benjamin, for your courage and your effort.
There is not much chapters on this, and it seems like it's a 48 minutes video. I'm going to skip it for this stream. I'm going to watch it offline. I think that's an interesting resource to cover. Go back to music and then open 97. Bit manipulation is a very powerful tool, also from Zig. Since the dawn of the computer age, numerous algorithms have been developed that solve tasks solely by moving, setting, or logically combining bits. Zig also uses direct bit manipulation, its own standard library for functions where possible, and it is often possible with calculations based on integers. At first glance, it is often not easy to understand what exactly these algorithms do when only numbers in memory areas change outwardly. However, it should never be forgotten that numbers only represent the interpretations of the bit sequences. Quasi, the reserved case we have, the reversed case we have otherwise, namely that we represent numbers in bit sequences. We remember 1 byte is 8 bits, is this format in binary, 255 decimals, and FF hex. Zig provides all the necessary functions to change the bits inside a variable. It is distinguished whether the bit change leads to an overflow or not. The details are in the Zig documentation section, table of operators. Here are some examples of how the bits of variables can change. Number 2, shift to right 4 bits, shift to left 4 bits. Okay. And or and XOR. Oh, okay. This piece I missed. I was confused. What's happening here? So number 1 shifted to the right. So this go to the right side, and meaning they get 0, and this comes in, and the unassigned bits will turn into 0. Shift left moves this to this part, and this and this, meaning everywhere that both of them are 1, it will be 1, or everything will be 1, and XOR everything but both sides being 1 will be 1. Yeah, this I haven't forgot that part yet, unfortunately. To familiarize ourselves with bit manipulation, we start with a simple but often underestimated function, and then add other expressions in loops. The following text contains excerpts from Wikipedia. Swap. In computer programming, the act of swapping two variables refers to mutually exchanging the values of the variables. Usually this is done with the data in memory. For example, in a program, two variables may be defined, thus in pseudocode, we can do swap, okay? After swap is performed, X will contain the value 0 and Y will contain 1. Their values have been exchanged. The simplest and probably most widely used method to swap two variables is to use a third temporary variable. However, with integers, we can also achieve the swap function simply by bit manipulation. To do this, the variables are mutually linked with XOR, and the result is the same. The syntax is, okay, do XOR. So now we swap values of the two variables by doing XOR on them. what happens when you XOR this, right? The XOR value of y and x will be stored in x. I don't get it. So what would be the XOR of this? It would be 0, 1, 1, 0. Right? And then it means to XOR these two and put it in X, right? And then the value of this would be stored here. And then we again XOR this with Y. And then the XOR with Y would be, let's put it like this. Y is equal to 1, 0, 0. This doesn't make sense. Now we swap the values of two variables by doing XOR on them. What must be written here? Let's do this, right? Comment this out. Let's see what's happening here. Zikron exercise 097. So X is 110. Was that what I suggested? Yeah. And Y is 1101. Yes, it would be 1101. What happens if now I XOR them again? Okay. And then Y X please. They're swapped. All right. Y is inside X, but X is not inside Y. I don't get one part of it somehow. So this. The missing line should be what? Okay, did I miss it? Then meaning we need to do Okay, thanks for explaining it to me. I figured this part, but I was confused with this one. So x, the first part is not necessarily to change. Or okay, we need to XOR this one. The Y setup would be fine, but we need to do it once more to fix the X. And then you have swap. I think this is how it's implemented in Python when you do A equal to B. And B equal to A. Let me check this because I remember there was an optimized syntax for it. Swap variables in Python. Oh, I like this. Yeah. This was the optimized syntax. So A, B equal B, A. Probably under the hood, they are using the same. So it requires less memory. You don't need to allocate a temporary variable. The variable swap takes advantage of the fact that the value resulting from XOR of two values contains both of these values. This circumstance was and still is sometimes used for encryption. Value XOR key to crypto XOR key value. Since this can be swapped arbitrarily, you can swap two variables in this way. For crypto, it is better not to use this, but in a sorting algorithm like bubble sort, it works very well. This was a nice concept. I think we resolved this as well. Yeah, let's go to 98. Another useful application of bit manipulation is setting bits as flags. This is especially useful when processing lists of something and sorting the states of the entries, e.g. a list of numbers, and for each prime number a flag is set. As an example, let's take the program exercise from exercism. Sorry, Pangram exercise from exercism. Probably it's better to finish this vlog after this exercise. I'm hallucinating. A pangram is a sentence using every letter of the alphabet at least once. It is case insensitive, so it doesn't matter if a letter is lowercase or uppercase. The best known English pangram is the quick brown fox jumps over the lazy dog. There are several ways to select the letters that appear in the pangram, and it doesn't matter if they appear once or several times. For example, you could take an array of bool and set the, yeah, it's like a counter, it means, right? And set the value to true for each letter in order to of the alphabet found in the sentence. However, this is neither memory efficient nor particularly fast. Instead, we choose a simpler approach that is a very similar principle. We define a variable with at least 26 bits, U32, and set the bit for each letter that is found in the corresponding position. Yeah. Zig provides functions for this in the standard library, but we prefer to solve it without these extras. After all, we want to learn something. Yeah. We have std, we have ASCII, we have print. And then inside main function, is this a program? Is this a Pangram? And then we want to probably return true is Pangram. First, we check if the string has at least 26 characters. We use a 32-bit variable of which we need 26 bits. Loop all characters in the string. If the character is an alphabetical character, then we set a bit at the position. To do this, we use a little trick. Since the ASCII letters in ASCII table start at 65 and are numbered sequentially, we simply subtract the first letter, in this case the A, from the character found, and thus the position of the desired bit will be found. Okay. Okay, we are finding the ASCII position. We are subtracting it from A, so we get a value starting from 0 and not 65. And then shift this U32 1 this many characters, and then OR them together with the existing set of bytes. Last, we return the comparison of if all 26 bits are set, and if so, we know the given. But what do we have to compare? What would it be? It's in hex, it means it would be FF, right? Do we want it to be FF? The last 6 bits are 0. So it would be out of 16, we will have 5, 6, 6, 7, 8, right? And then 1, 2, 3, right? This part will be, oh, this whole thing is an F, right? But last 6 up until here is like this. right? And then we have 1, 2, 4, 8, 16, 32. Am I missing something? We have unsigned 32-bit. And then we have F for 32, right? Or am I making a mistake? F is actually 15. Okay, I'm messed with binary calculation. Let's ask show me the binary calculation. So the answer is 0, 3, and then 6F. Here's the binary calculation. We need 26 bit set, one for each letter, A to Z. Let's calculate. Right, we have 26 character positions for 26 letter, and binary everyone is 1, right? Convert to hexadecimal, it would be 3. Let's see. Okay. And wait, let me recalculate more carefully. So every, oh yes, that's why I messed up here. Every 4 bit is 1, 3, 7, 15, right? And then you call this F, then okay, now I understand it. That's why it's wrong. So I have this, 6 times this, right? And then 3. Why is 3 here? It's because, yeah, I have 26 bits out of 32, so I need to have 6 zeros in the beginning, not at the end. That's also one of my mistakes. So yes. So the answer is this. Each letter sets 1 bit. Yeah, that's what I know. So the answer here would be 3, 1, 2, 3, 4, 5, 6. Yeah. Okay. Next one is actually interesting to solve. It's for formatting only. Let me see if I can remove this. Yeah. 97 and 98. So let's make it 200. 99. Actually, no, not that. 099. Formatting. Terminals have come a long way over the years, starting with monochrome lines on delivering CRT monitors and continuously improving to today's modern terminal imitators with sharp images through color fonts, ligatures, and characters in every known language, formatting our results to be appealing and allow quick visual comprehension of the information is what users desire. C set string formatting standards over the years, and Zig is following suite and growing daily. Due to this growth, there is no official documentation for standard library features such as string formatting. Therefore, the commands for format function are the only way to definitively learn how to format strings in Zig. Zig already has a very nice selection of formatting options. These can be used in different ways, but generally to convert numerical values into various text representations. The results can be used for direct output to a terminal or stored for later use or written to a file. The latter is useful when large amounts of data are to be processed by other programs. In Ziglings, we are concerned with the output to the console, but since the formatting instructions for files are the same, what you learn applies universally. Since we write to debug output in Ziglings, our answers usually look something like this. In addition to being replaced with foo in this example, the placeholder in the string can also have formatting applied. How does that work? And this actually happens in several stages. In one stage, escape sequence are evaluated. The one we've seen the most, including the example above, is \n, which means line feed. Whenever this statement is found, a new line is started in the output. Escape sequences can also be written one after the other. Okay, by the way, the result of these escape sequences is passed directly to the terminal program. Other than translating them into control codes, escape sequences have nothing to do with Zig. Zig knows nothing about line feeds or tabs or bells. The formatting that Zig does perform itself is found in the curly braces. Formatting instructions in the placeholder will determine how the corresponding value, for example, foo, is displayed. And this is where it gets exciting because format accepts a variety of formatting instructions. It's basically a tiny language of its own. Here's a numeric example. Catch 0x, and x is a hex representation of 22. We want it to be 0 padded, 4 characters to the left. And this formatting instruction asks, yeah, or you can center align a string like so. We do a star and then pad with a star, and this instead of shift right, it moves it to the center of the 20 stars. Let's try making use of some formatting. We've decided that the one thing missing from our lives is a multiplication table. For all numbers from 1 to 15, we want the table to be nice and neat with numbers in straight columns like, okay, without a string formatting, this would be a more challenging assignment because the number of digits in the number varies from 1 to 3, but formatting can help us with that. We have print, we have a size of 15. The error here is invalid string question mark. Okay. We start with a single X for the diagonal, header row with all numbers from 1 to 15. We are reserving 3 characters. 1, 2, 3. 1, 2, 3. Is that it? It should be including number. Okay, that we will figure out. And then header column rule. This is right align with 3 characters, and this character is not defined, so probably by default this is a star, and it's a digit that we are adding from 0 to 15. Header column rule line, and less than equal to size each time. Okay, this is going to be up until 15. We are going to create 15 columns, print /n. Now the actual table. Is there anything more beautiful than a well formatted table? 0 to size, we do A, and then print A, and then for each number in the row, so we go forward, and then here we need to do I think B. I'm going to do the same format as the above. Yeah. And then Zigron exercise 099 formatting. What's happening here is 1, 2, 3. So this is not similar to this one because the difference. Actually, it is similar. So there is an extra space, and then 1, 2, 3 is the number inside the column. How is that extra space happening? Let's try it. Do I don't know, like this. So only 3 characters added. There isn't a space here. Let's try this. So print, and then this A, they get printed back to back, right? That's true. But I have an extra space somewhere. Oh, here, I'm blind. Okay, I thought I need to get finish my deadline here. This is where the extra space is added. For some reason I couldn't see it. Okay, 99 also solved. Let's do 100 as well. Or no, I think this is enough for today, and don't think we have many more remaining here. Is almost yeah 11 more to solve, including 100. So yeah, hopefully somewhere tomorrow I will get back to the rest of it, wrap this up for good, except for async ones, which I need to spend some time and research what's going on there. Thank you for watching. Yeah, feel free to leave a comment, let me know of any resources that I can utilize to exercise my binary algebra as well. Yeah, have a nice day, enjoy your time.